Good afternoon. Before I introduce the speakers, I introduce myself first. I am Ramesh Anishetty, a retired professor at this institute. And it's a daunting task for our speakers to speak after lunch. I hope they're awake enough and enthusiastic enough to convince us of some interesting developments in Yang-Mills theory. The first speaker today is Professor R. Parthasarathy, who's been with this institute, I don't know how many decades, and he continues to be so. Please welcome Parthasarathy. The title of the talk is Quantum Yang-Mills Theory.
Good afternoon. I thank Professor Krishna and Dr. Ravindran and other committee members to give me opportunity to talk about my attempts in trying to understand quantum Yang-Mills theory. Professor Alladi suggested in 1977, when I joined here, I was working on nuclear weak interactions. He said, you should work on quantum field theory. That was the time of Weinberg-Salam model. And of course, QCD was just beginning at that time. So I took his advice seriously, and I am very thankful to him for the suggestion. Over the years, I studied QCD using background field method, and now all of you agree, people who know about the QCD will agree that to address infrared problems, you need non-perturbative methods. The question you can ask is, what is non-perturbative method? I don't think we have a good definition of that. To begin with, Yang and Mills in 1954 introduced an SU2 generalization of local gauge invariants, and this was based on the experimental observation of charge independence of nuclear forces, and therein lies its strength, not just hypothetical. Unlike U1 local gauge theory, in which photons do not interact among themselves, Yang-Mills fields talk to each other. And this is important, as we will see. Physics is where interaction is. The focus will be on non-perturbative aspects of QCD. So, though not fully understood actually by me, glimpses of encouragement are there. So, let me just begin with the classical Yang-Mills theory to set the background. The Lagrangian is known. It is invariant under local gauge transformations, but the equations of motion are highly nonlinear, as you can see that. And if you define in analogy with the Maxwell's field, the color electric field, color magnetic field, you see that del dot EA is not 0, del dot BA is not 0. I will come back to that. The Yang-Mills fields generate color electric charge, QA, and the QAs have an algebra generating the gauge transformation, and this introduces a chemical potential for Yang-Mills fields, and there is no chemical potential for photons, but there is chemical potential for the Yang-Mills fields because of this. And in my understanding, this was first pointed out by our chairman of this session, Ramesh, little later by Alfred Actor. The color magnetic charge can be written like this, and this chemical potential was, the importance of the chemical potential was mentioned in the morning by Professor Balachandran, but he was in a different higher plane than what I am now. And now this tells that there is no reason why colored magnetic monopoles do not exist, but we will see that they cannot be observed. We will see eventually. Now I pass on to the quantum Yang-Mills theory, and we need to quantize using functional methods. The methods used for electromagnetism do not work here. In fact, the Gupta-Broiler method will not work here, and you use Faddeev-Popov, which is a very standard procedure now. And if in a covariant gauge, the quantum Lagrangian is given by this, where besides the gauge fields, I suppress the matter fields except by the current J mu A. We have the auxiliary field BA and the ghosts. And I do not write the quark part of the Lagrangian explicitly. We can do it. But there are some differences. The differences are in applying axiomatic quantum field theory here. One is the space of fields expanded to include ghosts, anti-commuting scalars, violating spin statistics theorem. The Hilbert space has states of negative norm, so general methods of axiomatic field theory cannot be used here. Classical Yang-Mills theory well studied by mathematicians, but quantum Yang-Mills theory requires new mathematical methods to deal and with the expanded Hilbert space. Perturbative treatment of quantum Yang-Mills theory well studied by physicists leading to asymptotic freedom, experimentally confirmed by the running coupling constant. Non-perturbative methods for quantum Yang-Mills theory not yet been realized. There is an important property of Yang-Mills which is absent in the electromagnetic fields. They have the self-interacting property, which is a cubic, and derivative coupling, this is very important, and the quartic one. In a different context, the importance of cubic and quartic couplings, we realized, myself and my student who is here, Alok, and my collaborator Daniel K, inclusion of these terms avoided the instability in chromomagnetic vacuum. Now, so in the propagator for photon, we had electron loop contribution, while now we have Yang-Mills fields loop contribution also. This feature is responsible for confinement in QCD, as we will see. The quantum equations of motion are given by for the gauge field, and this is for the auxiliary field, and this is for the ghost, and you have the quark fields. Now, since we have fixed the gauge, we only have residual global gauge symmetry, which is the BRST symmetry. The BRST transformations are given here for the gauge field in terms of the ghost, and this is anti-commuting, this is like fermionic person. This is for the quark field, this is for the auxiliary ghost and anti-ghost. The BRST charge QB is an integral on over 3-dimensional space, and we can show that under BRST delta F mu nu A is not 0. You will keep it in mind. And therefore, the commutator of QB with the F mu nu A which is this object apart from an I factor, is not 0. So, this will be useful when we discuss observables in QCD using the Japanese Kugo and Ojima method. I had a nice time with Ojima in Kyoto. He was very nice. Unlike the Japanese, he was much taller than me. So, let me go to the what is called the cluster property, which states in a generic field theory, if phi 1 and phi 2 are generic fields, and in the limit mod x1 minus x2 goes to infinity, this splits up into two parts. And this was shown by Araki-Hep rule, cluster property. This holds in a Lorentz covariant local field theory with the unique vacuum. And there is a theorem of Araki. I quote this theorem without proof, but if in case somebody wants, I can try to give a proof of that. The theorem of Araki states that this object minus this object is less than or equal to some constant psi to the power of minus 2, psi to the power of 2n, 1 plus some ratio, and let me define this object minus this object as some superfix t, and psi is x1 difference x2, n is a non-negative integer, and we are considering case when there is no mass gap. If there is a mass gap, there is a slight change in the relation. Now, if suppose you can in the Araki days, 1960s, they applied it to QED, and then they showed that n is 0, and therefore this object goes like 1 over psi square or 1 over r squared, which is the Coulomb potential. But now we want to know whether n is 0 or not, and that's the whole problem. So let me define the Fourier transform of that difference as t hat t of 1 to of p like this. F is the Fourier transform, and again I quote a result. If the Fourier transform defines a measure, then n is 0, then you go back to the Coulomb case, and if it doesn't, then n is positive. Alright. Now I make some cryptic statements for a distribution d of p, which Professor Balachandran mentioned in the morning. To define a measure, the integral of d of p with any continuous function of compact support must be well defined. For instance, if delta of p is g of p for g constant and bounded, or it's a delta function, then d defines a measure. On the other hand, if d of p is a derivative of delta function in the momentum space, d does not define a measure, as if f of p were not differentiable at p equal to 0, then integral delta dash of p f of p is minus f dash of 0, which is ill-defined. So the Fourier transform of the correlator can be written as using Lorentz covariance as sigma alpha 1 to n q alpha of p t alpha hat of p, where this object is p of delta squared acting upon delta of p plus integral ds theta of p naught to make energy positive delta function rho alpha of s, where rho alpha of s is your standard Lehmann, Schelin, Zimmermann spectral density. In view of the measure, if rho alpha of s goes like delta function, then n is 0, and if rho alpha of s goes like derivative of a delta function, then n is greater than 0. Now that is the general result. So far we have not used any Hamiltonian, any Lagrangian. This is a general result. The Fourier transform of photon correlator, the U1 gauge theory, is integral ds over 2 pi s g mu nu p mu p nu rho 2 of s divided by p squared minus s plus Feynman minus I g mu nu psi over p squared plus I epsilon. And you see, this is the Fourier transform of photon correlator. On the other hand, the gluon correlator, which is we have it in non-abelian theory, d mu nu of AB, which is the group index, this is similar to what we had in the photon case, except this spectral density has AB as well as here, plus you have n is 0 to n plus 1 Cn of Cn AB g mu nu of delta square to the power of n plus dn d mu d nu times delta squared to the power of n minus 1 acting upon delta function. So, in contrast to the photon correlator, gluon correlator contains polynomials in derivatives of delta function. So, this feature by a theorem due to Bose, Epstein and Glaser for a tempered distribution, Fourier transform of correlator is a tempered distribution, implies that n is positive, n is greater than 0. So, we see that in quantum Yang-Mills theory, n is greater than 0, the derivatives of delta of p basically emerge from the classical Lagrangian, the cubic interactions of the Yang-Mills fields, and to the ghost contribution. In fact, if you happen to see the textbook by forget the name, fat book, Peskin and Schroeder, we will show that the unitarity can be proved only if you include ghosts. These two are connected to each other anyway. So, the cubic interactions, in the photon case, the self interactions and the ghost, there is a ghost, but it doesn't talk to the photon field, they are absent. I should mention here that the quartet mechanism of confinement by Nishijima is a partial result in the sense he relied only on the ghosts. There is a quartet mechanism of confinement. With n greater than 0, the correlator in the theorem of Araki goes like theta or theta squared, while in the photon case n is 0 and goes like 3 to the power of minus 2 the Coulomb potential. Now it goes like linear potential or quadratic potential, showing that the quark-quark potential is linear or quadratic confining potentials. Now we will go to the next section, physical subspace and observability. In quantum Yang-Mills theory, the total state vector space contains negative norm states. We need to define suitable subspace of V such that the S matrix is unitary. Kugo and Ojima suggested a subspace V sub physics of subspace of V specified by the states of V subspace is annihilated by the BRST charge. As QB generates BRST, the above condition expresses gauge invariance of the physical states. The vacuum is annihilated by QB, and so the vacuum belongs to the subspace. Now consider observables in quantum Yang-Mills theory. The physical space contains states with the zero norm, negative norm and the zero norm. The physical space contains zero norm. Define V physics mod out V0 and any zero norm state chi in V0 to be orthogonal to the states in V physics. The transition probability between physical states has the property, if you add chi1 and chi2 which belong to the V naught, it is not affected because chi1 and chi2 are orthogonal to the phi1 and phi2. Besides transition probability, physical quantities to be measured must be such that any state in V naught should make no physical effect in the measurement. To ensure this, if a zero norm state chi belonging to V naught were transformed by a physical quantity operator R to chi dash such that phi with the chi dash is phi with R chi 0 for some phi in V physics, then the measurement of R could be described consistently. So it is required that the physical quantity satisfy phi with R acting upon chi belonging to the V sub 0 should be 0, providing a definition of observable. Given QB commuting with an operator, let operator acting upon phi be psi. Since QB phi is 0 because phi is a physical state, QB acting upon psi will also be 0. So psi belongs to physical subspace. Since chi is orthogonal to phi and psi chi 0 and so phi O with the chi 0. So thus if any operator O commutes with the QB, then it is unobservable. We have seen that delta F mu nu A is not 0, BRST, which is QB with the F mu nu A, and that is not 0, and so the magnetic monopole in QCD, though it may exist, is not unobservable. A quark field with color index alpha has a BRST change. Delta psi alpha is a quark field is given by these TA are generators of the group and CAs are some constants. Since, ghost fields. Since QB psi alpha is not 0, psi alpha, the colored quark field is not unobservable. Consider the color singlet combination and you can show that QB with this color singlet combination is 0. So the combination color singlet is unobservable, which is a baryon. You can also show that mesons have this property. Thus we see that the observables are in asymptotic states, which is confinement in QCD. Now, is that all? No. There are certain issues. One, the defining expression due to Araki was obtained in 60s, mainly in the context of QED. It is to be studied whether changes are needed in Yang-Mills theory. 2. The behavior of d mu nu AB gluon correlator involving derivatives of the delta function is to be checked both by lattice studies and analytical methods. That's what I wrote to our friend Manu Mathur about that. The issue of mass gap is not addressed, which is relevant for the infrared QCD. I have no proof that this exists or doesn't exist, but I guess the cubic and quartic interactions will play important roles in deciding the mass gap. It is kind of an intuition that, like, in the case of Higgs potential, phi square and phi to the power of 4, which eventually gave rise to the mass for these fellows, the phi's are self-interacting. So perhaps in some context, the cubic and quartic interactions in some way may be able to provide an explanation or a mass gap in QCD. So this is, I wanted to say, I thank you very much. Thank you.
So I request the audience to ask questions to the speaker. Yeah.
Yeah. You said monopoles we can't see. Is it because they have some colored charge?
Yeah.
you
Delta
can't-
F mu nu A is not zero,
but-
and del dot magnetic
yeah.
color magnetic field is the magnetic charge.
But can't you construct monopoles which do not have color? They can.
How do you construct in QCD?
You just neutralize the color index A.
In the in the standard SU2 cross U1, you have a scalar field in the adjoint representation. So you can combine F mu nu A with the phi A. Here F mu nu A. That's it. But in fact, this question,
no.
hold on. This question, myself and my friend Vishwanathan answered it in 1982. We can construct a phi A, which is if D is the symmetric tensor of the SU3, D, A, B, C, F mu nu B, F mu nu C, and then we can combine that with the F mu nu A to define an F mu nu without A. That mimics the electromagnetic field, but delta F mu nu will involve again delta F mu nu A, and therefore it is not zero. Therefore it is not an answer. Beg your pardon? Yes, there are two monopole configurations because the rank is 2. Pardon? I don't talk about bundles. I only talk del dot BA is not zero. No, of course, it is not a monopole, magnetic charge. Okay, magnetic charge. It is not exactly a monopole, magnetic charge. Okay? Yeah.
I don't know any physics, so I'm very naive in my question. So if you go back to number 19. Okay, so I remember reading somewhere,
Yeah.
so there was a conference on magnetic monopoles, and then I saw the proceedings of this conference. And for that conference, they reproduced a best wishes letter from Dirac to the conference. And there he said, best wishes to your conference, but since formulating the theory of magnetic monopoles, I have now lost faith. I don't think they exist. But anyway, go ahead with your conference. So your statement there in 19 says, though it exists, it is not observable. So you're saying actually they do exist?
They do exist in equations. There's a del dot if the divergence of the magnetic field defines a magnetic charge. In that sense, magnetic monopoles may exist, but you won't be able to see. They're like quarks.
Yeah. So
Quarks
should you
do
not say?
exist.
So should not the word "though exist" may be replaced by "may exist"?
Can I just add a comment to that? So, it's in the context of Yang-Mills theory. The magnetic monopole is also colored here. Okay? But in the standard model, you can think of monopoles which have no color at all because there is an additional Higgs field and that helps you out in defining that. Okay? And in the standard model, you can construct monopole configurations which have finite energy as well, unlike in QED where it becomes infinite energy. So in his context, since they are all colored, they are there only in our equations.
Okay.
Okay. Please thank the speaker once more.
I request Professor Ramesh Anishetty to felicitate the speaker with Alladi Diary.
Thank you.
I think this is the unique sense, unique in the sense the chairman and the speaker, we wrote a lot of papers together on QCD.